So I think you've actually like I can revoke slides. Okay.
New slide deck has been shared. Or are you doing that?
Yeah. Can you refresh?
Yes, as soon as they're uploaded.
Good morning, everyone. Everyone. It may be morning, but for those who are still jet lagged, the true word is everyone.
We're just making sure that the slides are perfectly fresh. They're hot off the press. Still coming out of the oven, uploaded.
I mean, I have 3 more minutes. You're supposed to talk about something right now, right?
So it is now Tuesday morning, so many of you have probably seen the note well. If this is a surprise to you, please do go have a look at this wall of text by downloading it from the data tracker. Make sure you understand it. So we didn't really have any participation at the mic yesterday. Today, the reason that we are all here at 7:30 in the morning, thank you all for coming so early, is that we're going to have a panel discussion after this. Anything said in the panel discussion is a contribution to the IETF and therefore covered by the note well. So it's a rerun of yesterday morning slides for those of you who aren't here. It's still great to see you all in person. Thank you especially much for waking up so early to be with us today, 7:30. And if you're watching us on YouTube later, we love you too. So today's agenda. Yesterday, recap, basically a extremely informative and very enlightening. I learned stuff which I was honestly not expecting to do. Presentation sort of introducing QUIC and why it is and what it is and how it is. And today we're going to dig a little bit more into specific aspects of this. So Ian, with some help from Martin, I guess. Moral support from Martin. And slides from Martin. We'll be talking about some experience with deploying QUIC at scale. And then Lucas, who I don't see here, but he had to commute in, so he'll be here in a bit. We'll be talking about applying, observing, and debugging QUIC. And then after that, we're going to have all of our speakers come up for a panel discussion / Q&A. That is the audience participation part. So, those of you who are still waking up, you have either an hour to find your notes from Monday's session to figure out what you'd like to ask, or start thinking of your questions now and think of them as things go on. So with that, we will reload the slides. Reload the slides. With that, Ian is going to start telling you some jokes while we reload slides. It's 7:30 in the morning. You're at an IETF meeting, and we're at College Improv. Have fun, everyone.
Trying to think of my best QUIC stand-up jokes. I don't know. Oh no, that's nothing.
Hey.
Spin bet. Too soon.
They're not the newest slides.
I don't see them.
Are they still not there?
They're still not there.
Oh, okay.
You can do Ian. You want to do Lucas's slides?
What?
You can do Lucas's slides in.
Oh, I mean, I can start talking through some of it.
Yeah.
That's fine. Okay. So we're going to start with load balancing, or the QUIC LB draft. A number of you who are involved in the QUIC working group or have been to the QUIC working group are probably fairly familiar with the QUIC load balancing draft. But we just wanted to go over it real quickly because we're actively in the process of deploying it at Google. And so specifically, there are a number of things it potentially could really help us with, including linkability. But one major issue is when you have any cast, where you're using BGP to try to do load balancing for a single IP, potentially globally in our case. It's there are a number of complications. So one complication is if you ever want to change the weights on BGP or anything about the BGP announcements, of course, a number of connections like start getting sent to the wrong server, at least without like a good bit of extra work. And that's particularly true for QUIC. And you might combine with like a NAT rebind or something, and this makes this all like much worse. Another problem is also connection migration. So typically when you migrate a connection, when you think of like connection migration, you're migrating, say, from like cell to Wi-Fi or vice versa. So it's fairly common you're actually going to land on a different AS, an entirely different network. And as a result, it's fairly likely that you will actually land on basically like an entirely different peering point. Next slide. I'll go back one moment just to go through. So the agenda load balancing, and then we're going to talk a little bit about black holing or flow black holing. A fun little story on an outage that we had just about a year ago. And then like one slide on zero RTT and QUIC and why it's hard, as well as some information that you can go look at more if you want to care. So let's go to the next slide. Actually, two more. There we go. So this is essentially the situation I was talking about, where we have an anycast address. We're using an L4 load balancer, or in this case, like a slightly more intelligent L4 load balancer that is QUIC aware, and we're sending it to an L7 server of some sort, whether it's an application front end or another layer of load balancers or another layer of load balancers. And so again, if you have flapping or anything else, next slide, or connection migration, it's fairly likely you will end up on another load balancer. But yes, this is particularly true if you're migrating from cell to Wi-Fi, you're potentially changing carriers, and you're potentially hitting different peering points. And so this means that even though connection migration is great, it does not work nearly as well, at least in our infrastructure, for anycast as it does for unicast, where there's, basically an IP is tied to at the very least a physical location in a fairly strong sense, like a metro peering point or something smaller like that. So when you arrive at the second load balancer, it's like, is this a new flow? I don't know what to do with this. I'll load balance it like a new flow. So it's like all the old information is lost. We have a lot of servers. The odds you hit the same server is basically zero, and the whole thing fails. And migration will fail. So we'd really like this to work because we'd really like to move more traffic to anycast actually for a number of reasons. Additionally, it's like a very popular option for another number of customers. So next slide. That's one great reason to do QUIC LB and connection IDs. But there's also a kind of a discussion here. Oh, next slide. About linkability. And there we go. So
yeah, we got a fair amount of latency.
Oh, okay.
Screen share.
So perfect linkability is basically like anytime you have a single device connecting to a single machine and you can like track it the whole time. If you have a single IP, for example, and a single device, like that's perfectly trackable, right? Like it doesn't even matter if QUIC is involved or any other thing is involved. Like you're going to be able to track that connection because there's only one connection to that IP in the entire world. So that's kind of the worst case scenario. And but more typically what you have is kind of a good number of clients, next slide, connecting to quite a large number of servers, and asymptotically, this looks like perfect unlinkability. So anycast is actually helpful here in the sense that there's only one global IP. And so you have a lot of servers that kind of look like one server. And potentially you have something like, 1 million clients or possibly even more connecting to that IP at any given point in time. And you combine that with encrypted connection IDs from QUIC LB, and you start like approaching, some real vision of unlinkability that's quite strong. The word perfect is, it is asymptotic, but it becomes extraordinarily difficult as an adversary, short of compromising the keys. So it becomes quite a compelling proposition from a privacy perspective, as well as from a network infrastructure perspective. And that's why we're deploying it. So hopefully, probably Q2-ish, Q1-ish next year, if all things go well. And
sorry. Wait, hold on. No.
You got it. I got it.
No, you got it.
I have like, was the QUIC LB section clear? Does anyone have any quick questions before I move on now that we have like 2 seconds? Oh, yeah. I have, there's more of that to come. But thank you.
Are you doing the actual share?
I'm trying to do the actual share.
Oh, sorry, Quick LB. There's a draft called Quick LB that kind of describes this proposed solution. Yeah.
As you can,
I'm having connection problems.
I will do the share instead. There we go. So apologies, we had entertainment because there were
Martin Duke in the front row is the expert and as well as author of Quick LB. And so, you know, any super detailed questions, I will defer to him. And he will be on the panel with us. So,
Okay.
Um,
There we go.
Yay. Okay. This is the thing I was alluding to the entire time. So Quick LB has a single connection ID format that begins with 2 bits for config ID. So that allows like rotation of keys and some other things. It has what is called a server ID portion and a nonce portion. And the typical approach is that at least in the encrypted version, which is what we're looking to deploy, that this is basically like all encrypted. And this is all, except for the few bits and the length, this is all essentially opaque bytes to any passive observer. Yeah, but technically the draft allows for unencrypted, but I personally would not recommend that. And the marginal cost of doing encrypted, honestly, it's not particularly high. The worst part is just key distribution. That's by far the most annoying part. The actual encryption code is not that hard. So even an L4 load balancer.
So this means the load balancer, when the client has shifted setting of the Wi-Fi, is then having to do a unicast tunnel or something with the original server that holds that.
Different infrastructures are different, but the key fact here is when a packet that it does not know how to route arrives at any load balancer on Earth, as long as that load balancer has the keys that we have distributed to it in order to decrypt these connection IDs, it can decrypt the connection ID, look at the routing information inside of it, and do whatever the network infrastructure like needs it to do. So like at Google, we have a bunch of stuff that doesn't really make any sense outside of Google. And so like describing it would not be particularly helpful, but like, every different network infrastructure has information that they want to route by that's like, that they can pack into this encrypted payload. It basically is what I'm saying. Yep. Could be a tunnel, could be something else. Could be GUE is actually another common option as an example. Great. Next slide. Okay, let's talk about black holing. So this has been a problem for a while, at least for QUIC. This is partially historically due to some issues with middle boxes. I think most of those issues have been solved, at least to my knowledge, but nonetheless, the internet is a terrible place and black holing happens, and it's extremely user visible. This does also happen for TCP as well. And I know that there are some mitigations in the kernel, but I wanted to go through kind of what we did in QUIC to mitigate this problem. And next slide. And I also want to say that a 5-tuple can be black holed in either direction or both, but it's quite often actually just one direction. But it doesn't really matter because you can't really tell. Like, you can't really tell if you're not getting any ACKs because the packets aren't getting through from you to the server, or if you're not getting ACKs because the ACKs get dropped. It looks the same to you as the client. So another challenge is it's fairly common that for a given 5-tuple, that multiple paths on that 5-tuple or similar 5-tuples will work. Like the connectivity between like IPA and IPB is largely functional, but 1% of the flow hashes may be dropped. So it could be because you go through a bad line card. You could be going through like a bad router. You could end up, there's some load balancing going on and suddenly you end up getting sent through like some bizarre peering point that's like extremely far away and there's extraordinarily high packet loss. Like just things happen. And so it's not that uncommon for like, 2 endpoints to be largely reachable, but like either intermittently not reachable or otherwise unreliable. So the worst part about this is when you have black holing, typically you experience a timeout, at least by default, and you have to wait for the idle timeout of the connection. So this can be as short as 30 seconds, but commonly, could be a few minutes. This is extremely user visible and extremely painful. And so like having someone sit there and like wait for a page to load for a minute or 2 because, a flow happened to get black holed, though it's rare, is quite frustrating. And so in order to bring down tail latency, Next slide. Right now, at least in our implementation, we close the connection after there are 5 consecutive probe timeouts, under the theory that at that point, the odds that it's still alive are quite low. This certainly kills a small number of flows that actually are viable, but the vast majority of flows it kills are dead at that point. I think that turns out to be, when you do the math, at least in our code, at least like 10 or 12 seconds of time. So at that point, the user's probably quite frustrated anyway, assuming it's an actual user. And if it's a if it's an internet client like gRPC or non-user facing, then I mean, that's still an extraordinary amount of tail latency. And at that point, you're better off closing the connection and starting all over. So it does reduce tail latency, has some downsides. It's kind of unclear why this is so useful on the server as well as the client. We tried to just do it only on the client side, and it turned out doing it on both sides does help. I mean, I can come up with theories, but it's a little bit hand-wavy. So I don't really love this mechanism in the sense that it's a little bit hacky, but it does work and it does fix some fraction of the cases. The mechanism that we came up with more recently that I like quite a bit better, next slide. See, a quick solution. Got a joke in there again, is port migration. Oh, that's you, dude, never got resolved. That's nice. So the observation is that changing only port can drastically change the internet path that you get routed to. If you do a trace route from 2 different ephemeral ports on your machine, we've seen cases where you actually ended up going through different peering points, for example, which seems like amazing. In some cases, like you'll have like 9 hops on one side and 13 on the other or something. It's like drastically different routes. It's almost inexplicable. It's kind of like shocking how different they are. And so as a result, I mean, sometimes like if the connection gets black holed, like just try a different port on the client side. And it turns out this fixes the connection in a remarkably high fraction of the time. Like I don't have exact numbers and it does depend on platform. And I'll get exact numbers at some point in the near future once, maybe for a future IETF talk, but it's quite high. And it's, that avoids us relying on this 5 RTO or PTO approach of closing the connection and assuming it's dead, because instead of dying, those connections get saved and we have to use that mechanism less frequently. So this introduces entropy in both directions. So like some of the changes, such as changing like an ECMP flow hash in IPv6 in order to get like ECMP to change and getting entropy, which only works in one direction. This actually works bidirectionally. And so it doesn't matter which side of the path is actually being black holed in order for it to fix. And it's now default enabled in Chromium, which is Chronet, Chrome, and anyone else who pulls in the Chromium source code, which is a good number of folks. But yeah, it's quite simple mechanism, works quite well, highly recommended. Yeah, and a nice benefit of QUIC over TCP actually, because we've had similar problems at Google for TCP, and the solutions are much more challenging than just changing a port. As I said, IPv6, flow hash is like one of them. So, next slide. Excellent. Oh, so we had an outage last November, I'm fairly sure it was. And it was quite terrifying, actually. It was definitely like one of the scary outages. It turns out the impact will not end up being as bad as you might fear, but it was quite terrifying. So there's a query of death that was triggered by resumption information sent by GFEs, which are Google front ends, to clients, and then the clients would send the resumption information back to servers. So we talked about this yesterday with, how you get 0 OTT and such. It's a lot of like the server gives something to the client that the client then replays the next time it makes a connection. So like it's fairly standard stuff for QUIC. Unfortunately, this information sent by these new servers caused our server, the other servers, to crash immediately. So much so that the handshake never even completed. It got the client hello and immediately died. So at peak, it was around 10% of all GFEs or public-facing internet servers at Google. It's quite a number, but it was very uneven. It was mostly in Europe. And it took 1 hour and 44 minutes to fully resolve the issue, which is quite a while. The reason for that is actually mostly due to the SRE tooling and the impact on that. the reliability engineers actually did not have access to, and over the tools that they normally would have access to. There's actually like a lot more detail about that part of it in a recording I linked to you later. But for now, I'm actually going to focus on the technical bits because I think they're kind of interesting as well. Next slide. So we coined, after this outage, we coined this new idea called contagion, which is like an interaction of distributed systems. So a key point here is typically at Google, what happens is we roll something out, we canary it, say we send it to, in this case, we send it to only 2 machines, but typically, you know, send it to a rack or something. We test it, and if it starts crashing or doing something terrible, then we roll it back, right? Like standard stuff. However, contagion bugs, at least in this case, have the property that rollbacks don't work because there's now state distributed in things that are not your server and not the thing you are rolling back. So in this case, it was all clients on the public internet, particularly Chrome, and it turns out to be the worst one for reasons I'll get into later. But it's quite a number of clients that were potentially having to roll back, and you know, this basically we're waiting for these machines, people to like restart their browser or something like that before we can fully roll back, in some sense. So that's quite scary from an SRE perspective and a reliability perspective, because you know, rollbacks are like your friend. You're like, you assume that if you roll back the right thing, you will definitely fix it, and like rolling back the issue did not fix it. And that also means a single task can actually cause a global outage, which is the other thing that terrified everyone. So next slide. So an example, and one of the ones that happened in this case, is TLS or quick resumption. So again, you know, this is widely used. The server gives the client something that the client then repeats back to the server, and then the server parses it, and then, you know, if server A produces something that when server B parses it, it crashes or otherwise, you know, has undefined behavior, memory access, and so on and so forth, then you're in a bad place. This is sort of a unique outage in the sense that it can't be fuzzed in traditional senses, at least not particularly well. And it's not a 0-day in the sense that an attacker could take advantage of it. So as an attacker, you cannot craft a token or a resumption ticket that our servers will parse. It'll just not decrypt. It just won't work. So only we uniquely have the power to cause a global 0-day contagion outage of ourselves. It's amazing. With great power comes great responsibility. Okay, so next slide. So let's go through what actually happened to Google. I'll go a little faster through these because they're more visual, but they're quite fun. All right. So a browser does a handshake to what we call a canary GFE, which is a machine that's you know, using the latest software and/or flags. So completes the handshake. Get, you know, next slide. As I said before, a token is given to the client that you can use to approve your IP address for future use. So that's the source address token. You know, the client saves it. Everything's wonderful. In this case, the Canary jobs populated a new field that was mostly used for informational purposes. But you know, and so there's this new field that was shoved into this particular blob of data. But of course, it's all encrypted, so the client can't tell. Next slide. Again, token sent on by the client to the next GFE. This one does not have the new code. And additionally, the token should be cleared no matter what after doing this handshake because you already used it once. However, due to a bug in our IETF QUIC implementation in Chrome at the time, that did not happen. So it's sort of stuck around in the browser until a handshake completed. But unfortunately, next slide, every single time that token was given out, the server crashed, and so a handshake would never, ever, ever complete. Yeah, it just, yeah. So you basically have a poison token that will never clear itself. And the client will just keep like contacting servers and be like, I don't understand, like, why are you not there? Why are you not responding to me? This other person responded to me. Why don't you like me anymore? Next slide. And it keeps trying, and they keep crashing. Next slide. Yeah, exactly. So one of the good things that did happen here, like one of the few good things, is Chromium has this exponential back off thing where like if a handshake fails, it won't try QUIC to that domain for another 5 minutes. However, we were giving out tokens across like a whole host of domains for like the period of time that we were giving out tokens. And so, you know, a single client could still be crashing like 10 or 20 different, you know, services per like 5 or 10 minutes. So, you know, it's still quite a bit of impact for like a single client that happened to be given these tokens. Next slide. So let's talk about kind of the timeline. Next slide. Oh, that did not get exported properly. PDF fail. Okay, back. I'm gonna have to do this from memory. Okay, at 2:07 PST, so the middle of the night, server started crashing. The automated canary checks started noticing that servers were crashing. They instantaneously rolled them back after only 2 servers got the new code. This rollback took approximately 4 minutes. So 2 servers for 4 minutes had the mysterious code enabled on them. So at 031, everything was rolled back. SREs were looking at it, and they were confused because the rollback had completed successfully, and servers were still crashing. And additionally, they started realizing that none of their tooling worked. So all of their monitoring and everything, at least in the London office, was completely inaccessible. They couldn't access logging. They couldn't access crash dumps. They couldn't access. They could barely even figure out like how many servers were actually crashing or where. It was quite dreadful. And it took them a while to even realize that this was not, in fact, a global Google outage. In fact, the vast majority of Europe where this was centered had no outage whatsoever for google.com, youtube.com, and most major Google domains due to a quirk of how this particular like rollout happened. But for a while, they were absolutely paranoid and completely panicked. What they ended up doing is contacting some colleagues in Australia and New Zealand who were awake at the time, and had no problems whatsoever accessing these corporate systems because it basically was only crashing servers in Europe. And they like basically hooked them up with access. I think it also turned out that Meet worked perfectly during this time. So like they like once they realized that, they're like, oh, I'll just get like people in like another time zone to like get on a video call and like help me fix this up. So once they actually had access to everything, which is around 1:38, it took them about 5 minutes to figure out what the problem was and what to do, and like 7 minutes to roll it back. So you know, it was like a 15-minute outage and of the actual system, and about like an hour and 15-minute outage of all the SRE reliability and monitoring systems that they need to actually fix the system. And this was another reason why it was so lengthy and painful. Okay. Well, I will re-export these slides, so they're actually, what I just said is on there. Okay. So let's go to the last topic. So 0RTT is quite hard, even on a good day. It's particularly challenging in IETF QUIC versus Google QUIC. So you have things like multiple packet number spaces, which from a design perspective are great and have a number of nice properties, but they are quite challenging to get correct and make sure that you are retransmitting the right thing at the right time and bundling the right thing with the other right thing. And particularly if any single packet starts getting lost, what you should do in response to losing that packet is sometimes subtle. And if you get it wrong, you either end up with a handshake deadlock or something that takes so darn long to complete that your user will be very unhappy. So like a single packet loss at the wrong moment, if your algorithm isn't implemented correctly, can easily increase tail latency a few seconds, not a few hundred milliseconds. So additionally, the key management is less synchronous compared to like TLS over TCP. So in particular, the problem that Chrome had was Chrome had this thing where like it made the keys available when it were for handshake keys available when it got the server's initial and then it could parse the server's handshake packet and then acknowledge that and like continue through the QUIC key schedule. Unfortunately, there was a bug in Chrome where if certificate verification took longer than it took for the server's initial to come back, the event never got triggered to actually release handshake keys. You would never get handshake keys, and Chrome would just be like, I can't process this packet because I don't have handshake keys because like pouring SSL didn't give it to me. And like it would just sit there and like not acknowledge anything and of course the server was perplexed because the server had gotten its initial acknowledged. And it's like, well, you processed my initial, why don't you have handshake keys? But yeah, it was just due to a timing sequencing error. And again, like this is one of those bugs that like QUIC, due to kind of like the potential reordering events and stuff, I think is quite a bit more likely to have. So there's a whole talk on this, recording and slides that you can watch, and that's why I didn't go into it further. But there's some complex, sticky details in there. But needless to say, it's something that requires a lot of patience and a lot of debugging and excellent tooling. Without excellent tooling, I would say it's extremely difficult, if not impossible, to really get this right. Also, I'd like to say the first time we tried to enable 0R2T, it was a substantial regression compared to not having 0R2T. So do not assume it will be faster just because it's 0R2T. Even if your 0R2T success rate is like 70%, the 30% that don't work, if a bunch of them are like have terrible tail latency or something, it's going to drag everything down. It's going to make the performance worse. So like, please do not assume just because you enabled 0R2T that it will be a performance win. Really test it and actually like do the measurement and gather the data to like ensure that it's actually a win for your particular implementation. That being said, once it's a win for a given implementation, I would expect it to be a win for all applications using that implementation. So I'm not saying you have to like retest it per application, but for developers, I would just definitely be very cautious about that. And I'm out of time.
Thank you very much, Ian. And now, direct from the London Underground to talk about excellent tooling, we have Lucas Perdue. Do you want to share? Should I share? You already. It's yeah, that one.
That one. Good. We're gonna have a clock. Or...
I'll get you a clock.
Okay, I'll fill in the meantime. I was trying to think of a transport-related joke on the way in while I stood on the tube. All I'll say is my round trip time from here to home is about 8 hours, I think. So anyway, I'm Lucas Perdue. I'm a co-chair of the QUIC working group. I'm here today to talk you through all these slides about applying, observing, and debugging QUIC. I'm a little tired, so just bear with me in case I ramble a bit, but I've got a clock, so I won't run over time. So this is good. I wanted to spend more time talking about the applicability in this talk, but there was just way too many slides. So in the slide deck are a load of overflow kind of backup slides. Maybe if you have some questions towards the end or in the panel session, we could go back to those, or you go away and you're so inspired by this talk, you want to find out a bit more. So just keep that in mind. In this talk, we're just going to kind of probably touch on other topics that Martin, Jana, Ian, and Martin maybe touched on, but just from a lens of something's going wrong with my QUIC connections. I don't really understand it that well. I'm maybe like an SRE or an ops person, and I just need to figure this out. I'm familiar with TCP, I understand networking, but what can I transfer from my previous knowledge into QUIC, and what things shouldn't I do? Where do I need to retrain my brain? These kinds of things. So this is just going to walk through a couple of real world examples, literally something I was looking into the other week. It's a silly bug, but something that's been there latent. And so we looked at it. And so let's go. Next slide, please. But first, the important things, just to reiterate, if you haven't learned anything yet in these technical deep dives, QUIC is not TCP. There's lots of similarities, but it's different. And those differences are the kind of the places where you might stumble or fall. Next slide. Nor is QUIC just TLS. As we saw yesterday's presentation, the architecture and the interactions, the models between QUIC and TLS, you probably need to know some TLS. So some of the stuff we're going to look at shortly is going to get into things like TLS client hello, understanding around aspects of the TLS handshake, but not the timing and interaction specifically of those messages. It's going to be important because quite often when things don't work, they don't work from the first step where the handshake fails. So let's go. Next slide. And it's not HTTP. This is one of my bugbears. QUIC, yes, okay. QUIC was built to carry HTTP, but that's not what we have today. We have IETF QUIC, and it's capable of carrying anything you can imagine. Literally. You need to go, if you have an application, and create an application mapping. I'll allude to that later on, maybe more about what it means. But yes, it's not just HTTP. There are aspects of QUIC's design that lend itself well to bidirectional exchanges, but we have other capabilities to carry things unidirectionally, or we have a datagram extension that will allow unreliable message delivery. Don't make assumptions about your understanding of how HTTP works. And if you don't understand how HTTP works, that's even better because you can come in and take all these learnings away. Next slide, please. And it's definitely not the web over UDP. It's here for many applications. In our working group, we can help advise you if you want to use QUIC, but we won't be the gatekeepers for application mapping documents that describe how to use QUIC. Generally, the transport services it provides work now, modulo some implementation concerns, but it's here for everyone to use. It's not the only thing you should use. It's not, our panacea of everything, but it's definitely a tool to sit in your toolkit for internet. Next slide, please. And it's quick. QUIC is quick. Next slide. It's a secure transport protocol, which means we might have some issues trying to analyze it if we're doing things like packet captures. Just keep this in mind, that some of the things you might be able to do with TCP, where you're analyzing it with tools like Wireshark, they're not impossible, but they're different, and they might require different approaches. Next slide. And it's what you make it, which I've already touched on. Next slide. So if you haven't got the time for any of this, QUIC starts with a handshake. We have application data sent as soon as that handshake is done for some definition of done. Ian just talked about zero RTT. There's different effectively stages within the connection that application data can be exchanged, but it all relies on this handshake happening first. Post that, at some phase within that checkpoint, the packet's going to be protected. If you don't have the keys for that session, you're not going to be able to see the contents. You'll have a very slim sliver of information available in a header. It's tiny, and you can't just rely on that. And the other important thing, maybe it's been touched on already, but we have a reliable and unreliable application data. The reliable data is retransmitted in new packets. It's not retransmitted in packet being resent. This can cause differences in the way that packets and framing work. If you're familiar with TCP and you're trying to look for maybe particular byte offsets within a packet capture, this is not the way to do it. You're going to have to drill down into streams, and probably any application layer use of that stream or reframing or subframing on top of QUIC streams. Next slide, please. And we talked about applicability, management too, whatever we mean by management of a network. Maybe if you're just an operator of a network, then you're the manager. I don't want to get into that, but we have two excellent drafts that have been published in September, so fairly recently, but they've been developed alongside the core RFC specs, 8999 through 9003, and they cover two different aspects of things. You might not be aware of these documents. They're a really good read. If you want to get away from the nitty-gritty protocol details, which are good, but that's more of a reference manual. These documents are written for a different target audience. The first one of the applicability draft, RFC 9308, talks about the features of a transport protocol, how you might adapt your application, whatever that is, to work on top of QUIC, but not just an instruction guide, but the caveats, the considerations that you might need to make, where you have stream concurrency. That's a different feature compared to TCP, which had one single reliable byte stream. QUIC offers you a lot more things and a lot more ways you could hurt yourself, and a lot more potential for problems, say, where you have a client and a server that have a different kind of understanding about what concurrency means, for example. So it's an excellent document for that kind of thing. And then a completely different target audience in the manageability draft, which is more for people who aren't operating a QUIC stack entirely, but are seeing QUIC traffic flowing back and forth across their network. So this touches on the QUIC invariants and the QUIC transport protocol, and gives you effectively some explanation about what QUIC is and what QUIC will be, maybe how to analyze it, maybe how you won't be able to analyze it compared to other protocols that are traversing your network. So next slide, please. Again, let's go back. Everything starts with a handshake. There's all the places where handshakes mentioned. It's everywhere. It's great. This is already covered, I hope. But the key items here I want to focus on today are these two packet types that we have, initial and handshake. These are the things you'll probably see in the first 5 lines of any packet capture that you take. The initial is not a type, it is a type, so it's not an adjective. Sometimes when I talk to people who aren't familiar with QUIC, I say, we need to see the initial packet, and they think they mean the first one. But you get things like retransmissions or retries, reattempts to send the initial, and you'll see multiple initials. And they also hinge on the actor in the exchange. So you'd have a client initial, a server initial. Using the terminology, like I'm that person who insists on trying to use it correctly and to everyone's annoyance, but it's really critical here. And my understanding is we need to up-level a lot of people within the wider ecosystem, people like SREs or operations, to really, they don't need to understand all of the details, but when we're just communicating, can you help me see if the initial made it through the network and arrived at my server stack? These kind of conversations, people can be familiar with the TLS terminology, like did we receive the client hello? It's similar to this kind of thing. So that's one thing I would ask you to focus on and take away. Use the right terms. Next slide, please. So there's this excellent tool called the Illustrated Guide to Stuff. I can't remember the right name. There's a link here. It covers not just QUIC, but TLS 1.2, 1.3, I think. This is a visualization of actual kind of simulated data. If you go to that website and the repo behind it, you'll see that they use kind of real client-server interactions and take PCAP and then take those bytes. So you can see here, I've just tried to point, the text is small, I apologize, but there's a lot of stuff going on. I do encourage you to go visit it, but you can see there's two different initials within this vertical trace, the client initial and the server initial. The arrows there kind of pointing in the opposite directions. So if you go to the next slide, each of these boxes you can expand, and it's really meant as a learning tool. This isn't a debug tool. The bytes here, you can, like I say, you can go into the GitHub and they're canned, and you can go and understand exactly, maybe you want to go and fiddle or do other things. Maybe you've got some comments on the additional kind of annotations you might like to see, but you can open up the client initial, you can view the TLS client hello within that client initial, and then drill down into different bytes there. So it's good if you just want to say, maybe take an existing trace and compare it to kind of a reference example. So next slide, please. Just to drill even further in there are these transport parameters. These are the properties of say a connection that each endpoint will advertise to its peer. We don't have time to go into that. But if you're like looking at a packet capture and you're drilling down and you see these transport parameters and you think, what are these? Go and look in IANA, they should be registered there. Maybe not, but this will give you a brief overview. Most of these are in RFC 9000, but we have things like extensions, which would use transport parameters. These kinds of things might be new to you. You might say, I'm seeing some kind of issue, and it could be related to a mismatch or an impedance there. You can see on the right-hand side is this full expansion of what all these things mean. Next slide, please. So let's look at an illustration for live connections. We just looked at some pre-canned examples. You can use your old friends, PCAP and Wireshark, to look at this. To just successfully dissect QUIC packets, you're going to need a version of Wireshark 3.4 and upwards. The examples here for the remainder of this session are just created using Cloudflare keys. So I work for Cloudflare, it's the client and server I'm most familiar with. We have some example apps in the repo. Pretty much any other client is going to be very similar to this. So if you have a favorite, you could probably recreate these things. But just in this example, I have a server running on localhost. These flags effectively minimize the handshake. They just reduce a few steps for clarity. If I didn't have that no retry flag, for instance, it would send an additional message during the handshake. It's all cool, but it's complicated and we don't have the time. So you can kind of ignore those things, but yeah, this is just a request on my local host to get an index file. And that PCAP underneath what you see is very small text and you probably can't see it, but that's kind of the point because I want you to go and look at this yourself. But the first packet or the first line there is the client initial going towards the server. And then we have some stuff coming back in the other way. It says handshake there, but we're going to drill into that next. Well, one more. So I have some ready-made examples. Speaking with Brian, we thought it would be cool to take some live real things that I captured and put up on GitHub. These PCAPs and QLogs that I've got for localhost good, just a simple good exchange of a request that succeeded at the QUIC layer at least. So next slide, please. Again, too tiny to see, but if you opened up Wireshark and you clicked on your first line and you expanded out all the details, you're going to see a few indicators here about what is the client initial. It's easier. It's a lot easier here because we've only got, a very small PCAP of one interaction, and we already know that. But if you're kind of trying to find a needle in a haystack, trying to look for some of these things, it can be a bit difficult. But yeah, we've got indicators like the source port or the destination port. It's a bad indicator using source port. Don't rely on that being anything. It could be the same for everything because QUIC is clever. But alongside that, within the packet type information here, we've got dissection to tell you the type based on stuff. And underneath, within the contents of the client initial, we have the client hello. So this is the TLS client hello message. Again, zooming in, we see the transport parameters. This is exactly the same as the other slide I showed you, but these are the actual transport parameters that the quiche client sends in this case. Next slide, please. Important thing here is application layer protocol negotiation. I don't really have the time to get into this at all, but in this case, what happens is the client's going to send a whole set of different variants or versions of HTTP that it talks. So it's like an offer answer protocol, and this is it. You might see different lists, different sets of protocols in there. If you're writing your protocol, you should definitely make an ALPN for it, because it helps you allow multiplexing of different applications. Maybe if you just want to set up one quick listening port and support a slew of applications on there. This touches on the applicability draft. There's things you should consider around transport parameters in relation to the application protocol you're trying to negotiate and where things might not completely converge, but that's another talk for another day. Go read the applicability draft. Next slide, please. In a reverse direction, we have a server initial and a handshake. And you can see in the top, the indicators are kind of similar. The source port is the server's listening address that we showed in the line a couple of slides back. We have the initial type again indicated, and then just below that we have a server hello coming back. But we can't see as much information as we could in the client initial. We have this server handshake packet just underneath, but you can see it's been quite clear there. We can't decrypt anymore because the secrets aren't available. What does that mean? Next slide, please. We need the keys. We need the keys to see the full picture. From even in that early stage of 1 and 2 interactions going in opposite directions, we might not be able to see everything that's happening that would help us diagnose some kind of issue that might be happening early in the connection. You're probably familiar with something called SSL keylog file, but if you're not, it's used by many, but not all implementations. Endpoints can be instructed with like an environment variable, or maybe just built or configured to place their keys explicitly in a location that can be used to contain the session keys in a format. This is kind of common. It's a de facto standard. Martin's been working on a new ID to kind of formalize this format, which is good work. But the session keys are symmetrical. So if you can drop them from the server or the client end, you should be able to decrypt the packets for anything. So depending on who you are, what you're in control of, sometimes you can use this as a kind of, I need to see both directions of traffic. In this example, like I said, we're just using an environment variable to dump some keys into a file locally. We can configure Wireshark to pick that file up. Next slide, please. So I can't go into it, but yeah, the Wireshark documentation will explain this. You can go into your preferences, or there's all kinds of cool tricks you can use. But once you're configured, once it finds the correct session keys for an interaction, this is again, the same kind of dissection I showed earlier, but this time that handshake packet is revealing a lot more information. It's showing the ALPN, it's showing that in this case, the server picked H3. So from that whole list of things, it picked 1. Next slide, please. If we revisit the kind of complete picture, not just the one packet, we can see the dissection without the keys. There's some, the top 4 lines, too small again, sorry, but we've got some packet types, and then it kind of converts into this protected payload where we can see a field called the DSID. I'll explain that in a couple of slides, but that's it. If you click those things, you're just going to see opaque bytes, and you're not going to know what they are. With the dissection, well, with keys, you can see that we actually can drill in now. We can see different packet types, packet numbers, frames within those packet types, stuff around streams, acknowledgements, crypto, etc., etc. Next slide, please. And then I touched on SIDs. These are connection IDs. If you look in this example, we're going to see different connection IDs going in opposite directions. This can be useful if you're just trying to trace connections of a particular type. Again, if you're trying to find a needle in a haystack. Next slide. So that's Wireshark, and that does one thing well, especially if you can dump the keys. But we have something called QLog, which is like my colleague Robin down the front has been working on for a number of years. He'll tell me my description is rubbish here, so go and speak to us at the end, and we can inform you everything. But the implementations often have debugging or logging of their own to augment stuff like packet captures. You can see kind of the reason why something happened, not just the fact that it did happen. And a common logging format can encourage an ecosystem of analysis and tooling that isn't just specific to an implementation. So what we have in the QUIC working group is adopted working items for a kind of core base schema and CDDL. This is very extensible. We can use that extensibility to define concrete definitions. At the moment, we're just focused on QUIC and HTTP3 related events because that's what we've worked on. But other kinds of things can be added. So if you're adding application mapping, you can, maybe you want to define some QLog events. That's something that we're trying to figure out this week. What's the right level of guidance to give to people? But it's extensible. It's just logs. It's just kind of text. You can stick stuff in if you know how to read it, if you know what to look. But what's nice is the current fleet of QUIC implementations, many of them do support QLog. So if you're trying to find a bug between client and server implementations and you understand like what stack that is, say it's curl built with HTTP3, you can enable QLog and get this QLog format out and stick it somewhere. That will help you analyze and maybe fault diagnose more quickly or understand what's happening with a congestion window. Next slide. And we have QViz, Robin's lovely QViz tool, which I would just describe as trying to make sense out of oodles of data. If you went on the GitHub and grabbed some of the reference material I had, you can go to this tool now. You want to do for option 2 upload a file. It's not an upload. It's kind of all client hosted. For what we would analyze today, at least. So it'll happen in JavaScript in your browser and come up with this kind of excellent sequence diagram. Again, way too small to see the details here, but this is effectively rendering the same information we just looked at in the Wireshark in a different way. So this is going to give you maybe a bit more of a context-aware view of packets exchanging between the client on the left and the server on the right. Each line's a packet. That's my interpretation. Again, Robin, correct me at the end, but within those, you have the frames. We have kind of a very quick summary view of what those frames are. And then if you click any of those boxes, it's going to give you an expanded view. Again, this is a real example, but it's a good learning tool if you're just trying to get familiar. If you're not somebody who can read a spec in one go and walk away and understand everything. If you're a bit more like me, a bit more practical, and you just want to run some stuff, try some things out and do this. Next slide, please. So I just want to look at a real world failure that we had. Again, this is using SSL keylog file. They're great. And no, the box is in the wrong place. Oops, sorry. Yeah, it's using SSL keylog file, amazing. But there's a property in HTTP3, you need to be able to open some unidirectional streams. Again, I don't have the time to go into that, but you can configure this quiche client, this example application to advertise from the client to the server a value of 0, that it can open 0 initial unidirectional streams when the handshake is complete. Our server code doesn't like that. It wants to be able to open these streams, and if it can't, it will detect the error in the code and send a connection close message. So an explicit, immediate close from the server to the client to say, I want to open up the control stream, I can't, sorry, like go away. This is the kind of thing you should probably be looking for if there's ever a report of an issue. Stream resets, connection close messages are kind of good, strong indicators of what happened, but maybe not why. Next slide. Same failure, same trace effectively, the QLog captured at the same time, a different rendering. You can see here the connection close is in the bottom in red. That's as much as you can see because of the rendering, but yeah, it might be a better way to view these things. Next slide. Another one, another failure. This time pretty much an identical command, but for a different host name. So the last one was to localhost, and this time to my website. And in the packet, well, the PCAP looks a little different. Just from a mile kind of view, it's different, which is always a good sign of if the behavior is different. If someone's saying this behaves weird for this thing and not that one, and you see a PCAP that's identical, that's annoying. But if there's something like this, that's immediately, there's a change in behavior, that's a good signal. So here it's like, where is that connection close? I told you what the behavior was, what we were expecting, we're not seeing that. Why? Next slide, please. QViz, it's even worse. It's even smaller, you can't see it. The indicator here is it's really long. There's a lot of things going on here in terms of timing. There's no collection closed. Received by the, oh, there's a bug here. It's received by the client, not the server. But anyway, next slide, please. So what's the difference? You know, we've got effectively the same client behaviors, just pointing at two different endpoints. Are they a different implementation? Are they different stacks? No, like they use the same underlying stack in this case. I know that, but that's because I've got insider knowledge. What's the root cause? What could this possibly be? And that's what I had to spend some time on the other day looking into. Next slide. There's different types of connection close. We haven't got the time to go into this, but you have a transport layer and an application layer and code, and they send different types and stuff. Next slide. So the root cause here is a trouble with timing. The HB3 library that we use for the server side, like I say, it sees a 0, doesn't like it, calls close on the transport layer, passes it an application layer code and a reason. But neither the application or the HB3 library checked the transport state. The handshake had completed correctly at that time. So this doesn't happen unilaterally, but there's some timing differences that I found. And because there's a potential leak of information, of application layer information before the handshake had completed, the RFC says don't send it, you know, send something, you can strip some information so that the peer is going to receive that explicit close and know that something went wrong, but not the specific details. But there was just a bug. And so the server didn't send that. The client kept retrying, not retiring. That's what I want to do. But eventually the idle timeout kicked in and it gave up after several rounds of retry. Next slide. And so that debugging, given I had some tooling and some knowledge of where to look, quite quickly I was able to kind of turn that into a unit test, come up with a fix, which was a one-liner. And now the client will always receive a timely close. Next slide. So yes, in summary, it works if you know what to do. And that's what I want to make sure that we can scale out our understanding of QUIC, our ability to use it. It's one thing having a spec on the shelf. Great, wow. But we want people to use this. QUIC isn't TCP, it's not TLS, it's not HTTP or the web over UDP. It could be anything that you would like it to be. And there might be use cases that you need to use that might need kind of slightly different approaches to debugging, but generally, in my opinion, stuff to do with the initialization, the handshake is kind of the first step in everything. There's minimal information available on the wire, CRFC 9312 for information about how to observe QUIC if you're not as kind of involved in the interactions between client and server as you would like. And just be aware that implementations and deployments can behave differently. Sometimes there's bugs, sometimes there's a lot of things deferred to an implementation choice, you know, how shoulds, kind of level of normative requirement, and just opinions of the operators. So don't assume too much. Don't assume that the implementation is perfect or that a behavior that you see that seems weird isn't done by intention. And there's ways you can kind of get some logs to do this. That's it. I'm done. Thank you.
Thank you very much, Lucas. So I will ask all of our speakers to come up. Good morning, Jonah. Lucas, you too.
Oh, that's gonna be cold.
And actually, if one of you could grab the mic and we'll do the pass the mic thing. And if you have any questions for any or all of our speakers, please put yourself in queue and come up to the mic now. I'll give people a couple of seconds to figure out what they want to do before I start asking my own questions. I know it's early.
Yeah, questions.
For remote people, can you like actually put yourself in queue? I mean, you go ahead and say your name, but like we do want to make sure we refer to people who are not here.
My name is David, and I guess question for Martin Thompson. I probably could have looked this up myself, but I think you mentioned that you initially tried to use DTLS, but then it's a bad idea. So now using TLS, but QUIC is UDP, so is TLS TCP or UDP? I got confused on that point.
Such a juicy question.
That's a fun question. So we initially thought that maybe the handshake could use the DTLS mechanisms for reliability, and we would just do DTLS to start with, and then we would get to do quick things once DTLS is done. Unfortunately, DTLS doesn't have the sort of really sophisticated recovery mechanisms and all of the other things that QUIC has, and so you get a lot more advantage from building all of the reliability and in order delivery mechanisms on top of QUIC, and so that's what we've done. By doing that, we were able to use TLS, which is a much simpler protocol, and so we avoided all the DTLS machinery necessary to do reliability and fragmentation, reordering, and all those sorts of other wonderful things, and just use the stuff that we use for reconstructing streams in QUIC. And that turned out to be much easier in the end, as it turns out. Once we made that decision, it was very straightforward to use all of the QUIC machinery for managing packet loss, recovery, order delivery, and whatnot that TLS uses. You want to add something?
So yeah, you get the advantage of you can use like a sort of a single software architecture, and the disadvantage is you get a really wonky layering diagram, right? I think it's like, and we spoke about that early on. It's like, ooh, this layering diagram looks weird. There must be something wrong here, and it turns out that it was right, because otherwise you have to have TLS or DTLS or whatever.
So yeah, I mean, I think we've always held that the layering diagram should follow reality. Reality shouldn't follow the diagram. And in this particular case, it was very obvious that actually having a separate loss detection recovery machinery was going to be fundamentally suboptimal. It's not something you want. If you have a big data stream and you have all the mechanisms built in, you want to use the same one for all the data that you send, not just for the handshake data is not special in this particular way.
Cool, thanks, David.
Tail, I apologize that I suspect that this was already addressed and I missed it, but what's the current status of the original Google QUIC implementation with regard to the IETF implementation?
We are attempting to turn it down and remove the code as soon as humanly possible. It is a very, very high priority of my team. The expectation is Q1. It may be off sooner for certain other properties. So like YouTube might go down, like turn it off earlier and stuff. But it's either going to be very end of Q4 or Q1 that you're going to start seeing it being turned off. Hopefully the code will be delayed by the end of Q1 if I'm really lucky, but it's a lot of code. It might be Q2.
So yeah, hello. I'm Esker Dijk. Just a quick question about QUIC and using it over nets and firewalls, etc. Is there any special consideration or things you have to do, let's say, to keep a connection alive? I'm just wondering about that.
I mean, yeah, just don't black hole the connection after the handshake. It's a bummer to debug. And it's very bad for user experience. Like if you're going to drop like a quick handshake, just don't let any packets through. Because remember, one packet in each direction is enough to complete a handshake in some circumstances. And so like we've had issues with packet inspection where like some of them are like, I'm going to take a few packets to figure out what flow type this is. And it's like after 3 packets, it's like, I don't think I know what this is, so I'm going to just drop it. It goes terribly. These are strands is dreadful. So don't do that. Besides that, like I think a lot of things are quite acceptable.
Yeah.
Oh, there's also information in the manageability draft that's actually quite good.
Yeah. So the manageability draft talks about from the client or server side when you potentially have a middle box on the path that's doing that or firewalling, and as long as they follow the advice that Ian talked about there, then things will work. What we do find though is that some NATs will time out faster than the connections will time out. That's okay. The use of connection IDs will ensure that connections will still manage to work. It looks like migration at the server, but everything just sort of works out reasonably well. We don't recommend that people do keep alives. Keep alives are useful in very narrow circumstances, but in most cases you won't need them. It is better to just walk away from a connection and never send any other packets if you don't need it. And we've found that in particular when you're dealing with mobile devices, that's excellent advice, because you don't want to wake the radio up just to say that I'm going away. Just walk away.
Just to add some context, because I think it may not have been clear. Browsers currently rely on TCP as a backup if QUIC fails. So if the QUIC connection were to fail, the user would not see a problem, would be able to fall back to HTTP2 and TCP, and that would work just fine. That's currently something that we do across the board. The problem is if QUIC doesn't fail, QUIC succeeds, HTTP3 succeeds, and then fails eventually, that's a harder one to debug, is the basis for that. Now, the one thing in terms of keep alives and other things is that a NAT cannot do much in terms of adding to the connection, right? A NAT cannot send keep alives. A NAT cannot do any of those things. A NAT cannot send a reset. These are things by definition just part of the protocol. It's all end-to-end encrypted, and that's one thing. But yeah, the things that the NAT can do are things like dropping in odd places or things of that sort. But those are the things to be mindful of.
One thing I'll add is, as stated in the manageability draft, if possible, if NATs could actually conform to the RFC, and I use the, I think, 2-minute minimum idle timeout for NAT rebinding, that would be, that's sufficient for like, I think the vast majority of use cases. But if that would be my like ask, is like, ideally, if they could do that, that would be wonderful.
Hey, just to add, John touched on TCP fallbacks. This works well for HTTP, but QUIC is not just HTTP. So if you're designing another application to go on top of QUIC, you might have different world or different considerations. Maybe you're taking something like that already works over TCP and you're mapping onto QUIC. The applicability draft gives a good section of considerations about the need for a TCP fallback, but not the mandate. And gives a color commentary about these kinds of trade-offs, which are illuminating.
Okay, thank you.
George Michelson, can I shift target a little bit, which riffs on what you just said? I realize 99.9999% of the world is HTTP, and I would approve of targeting the thing that will make everyone happy and money. But I live in SSH and MOSH, and I sit here wondering, why isn't there a shim layer library that simply allows me to do single packet transactional work reliably across address mobility, taking care of this stuff? Why hasn't there been an interface spec that gives me a command and control interface for a machine that runs over QUIC? And S-tunnel exists, so it's not like people don't understand how to do SSH over TLS through hacky abstractions. But couldn't you code a shim layer that just gave me transparently access to this framework to do zero RTT, low latency, protected access, walk away from it, come back on a different IP and carry on the session? This is what MOSH does. But I don't want to run a Perl user space daemon to do my terminal binding. Where's the shim? Where's the equivalent of trumpet WinSock that gives me ubiquitous access to this software?
That's off topic, right? That's the quick answer is sorry, that's off topic.
Lucas has got it and John is up and I'm going to put my hand in too. So go ahead. No, Lucas, go.
I'll give you the short answer, which is the person who wrote Mosh is now, I believe, a Stanford professor and probably has like much less free time than they used to. Yeah, I think it's a very valuable concept.
I mean, it's Mosh solved a problem for all of us, right? And I mean, it did solve a problem for all of us. And the fact is that that mobility is something we want. Session mobility is something across the board, is something you want. I mean, but as Martin's pointing out, I think that the protocol offers the facility for doing it. There's absolutely no reason to not move.
No, but the essential quality in the very badly worded question is there is a significant barrier to entry unless you sit in HTTP mode and think, oh, well, QUIC is just HTTP. I'll use QUIC. Well, it's not just HTTP. And your comment went to, if you are running in different contexts, you may have to do TLS failover. And I'm sitting here going, I have to code the TLS failover? No, you should be coding the TLS failover for me. It should be a transparent shim function. I should not have to perform that function.
So
Maybe.
respectfully, this is not a service organization.
Yeah, but you know what I mean.
That software.
You know what I mean.
This is not really a question for us. This is a question for the audience. Please, someone provide George with the
yes
with these capabilities. We would all love that very much. Some of us are doing other things at the moment, so maybe this gentleman here will do it for us.
Well, hold on. I want to do. I do want to. I thought one of you was going to say the following, but I think Mask is tomorrow morning, right? And Mask is about 80% of what you want put together in a different way for a different use case, right? So, like, I'm not saying use Mask for Mosh, but if you basically reorganize the bits of Mask, you could build a Mosh, and all of you, let this be inspiration, as Martin said. Like, the tools are there, the bits are there. We're still learning how to assemble them, and I think that we could very easily assemble something that looks very much like what George wants from parts we mostly already have.
Yeah, but I do want to reiterate this fact that we've done the work so far, and we explained the protocol. So go build the damn tools. And this is out to all of you, right? I mean, it's all of us as a community to build this.
Yeah, Phil Harnbaker. I was going to say, yes, I am working on something like that, but it's going to be a long time before it works over QUIC. In that, first I've got to work out how to do exactly, got my transport layer fixed, then work out what the API needs to be in order to abstract an agile cryptographic transport or whatever. And then finally, I'm not using QUIC at the moment, I'm using my own stuff. I'm going to have to work out how to map that onto QUIC. So it's going to be about 12 months before I have something that will do what he wants. And then it's probably going to be another 24 months after that before we work out how to do it on QUIC. I mean, I think it would be very valuable to abstract down and work out how we apply QUIC-like transport directly to web services and get rid of HTTP, because HTTP is a really rotten way to do an RPC interface. There's a huge amount of overhead, and I'm speaking as one of the original authors of HTTP 1.0 and the person who originally made it possible to do that. It's what I want to do is to take those parts of HTTP and put them into the transport shim. So, but it's going to take time.
So yeah, there's the QUIC working group is not going to produce a QUIC API. I think there's enough divergence in the many implementations that work that it's just not going to converge. There is, however, the TAPS working group, which is working on abstract transport layer interfaces that support all sorts of the advanced functionality that transports like QUIC provide. And so I would really encourage people interested in a more generic API for this kind of stuff to take their energy there.
So those documents are mostly done. So take your energy there means please comment on IETF last call. Oh, true. There is still the QUIC mapping to do.
Yeah, so it's not just HTTP. We have DNS over QUIC, which is defined and it's a thing. And you might say, well, it's natural, we'll just fall back to TLS there. But that might not be what you want, right? You might want to fall back to DNS over HTTP. I think it's very easy to assume that we can build a batteries included API and library. Those things could exist. They could be powerful, but sometimes they behave in ways that you don't want, and there's no hooks or configurability to change things because the needs of your application are different. Presuming there's always going to be a TCP equivalent to your application protocol is like, that's just a guess. We don't know what those are, and trying to anticipate is a bit rubbish. So we have some of this going on in web transport where, you know, we have different ways to carry this thing. Some are UDP based over QUIC, and they want to use the service of unreliable message delivery. And so if that isn't available, falling back to a TCP-based fallback isn't going to give you that same transport feature. Is that really what applications want? Or would they prefer to give up and fall back to something like WebRTC? That might not be ideal, but they would prefer that. Possibly, we don't know. It's kind of impossible to anticipate all of the application needs. And being too opinionated is maybe giving people a disservice there.
And actually trying to allow applications to model that is where a lot of the complexity in the TAPS interface comes from, right? Like that's the hard problem.
So there are two things here, right? One of them is that there's the network, and then there's your application that you want to run on top of QUIC. So in terms of what you want to build here, this is what I said yesterday in my talk. We built using HTTP because it was an excellent vehicle for us to get this out there. But the work that's happening now, DNS and others, and also mock, which is also happening later this week, all of this are, you know, work that's going on and trying to map other applications and protocols on top of QUIC. Finally, in terms of the network itself, we know for a fact that there's a small percentage of the network that doesn't allow UDP, or, you know, with experiments, we found that QUIC doesn't work on 100% of the paths. That's also an application choice. Your application can absolutely choose to say that it's okay. If it doesn't work, it doesn't work. The application doesn't work if QUIC doesn't work. You don't need a TCP fallback. And that's all up to the application.
And I think we have a question from Tony Lee, who is remote, I think.
Some of us are thinking about migrating a strange application to QUIC. This application is called BGP, and we'd kind of like to not mess it up. Do you have any idea where the potholes are going to be?
Where are the potholes? Where are the potholes for putting BGP on QUIC?
I'm aware of multiple BGP over QUIC drafts, and I've skimmed. They seem to be fine, to be honest. I don't know enough about BGP to comment, but you know, the QUIC working group is here to provide some feedback, so we can do this formally. Absolutely, if you want to come and ask for like an early review, this is the kind of thing that personally I'm always happy to do, but I think people in the working group, because we don't want people to try QUIC and then it fails. Trying to preempt what those problems might be is difficult, but kind of the typical ones for me would be flow control, connection level and stream level flow control. How big are the messages that you're exchanging? You're going to find some way to get not deadlocked, but not perform as well as you might do. Multi-streaming in general is a big issue here. You're using QUIC probably to make use of the multiple streams in the one draft I read. How do those things actually interact at the application? Can the API from the QUIC layer and your application work in such a way, for example, there's no global ordering of streams in QUIC. It's done by design as a performance improvement, so we avoid head of line blocking, but can the application manage out of order delivery? You can send them in the correct order, but the network is the network and they might arrive in a different order. If you're depending on specific ordering between things, at the application layer, you'll need to accommodate that in terms of synchronization or checkpointing or however you might need to design. If you have more atomic messages like DNS over QUIC, where these things are very independent, it's a good mapping. Just stream credits. So we talk about flow control, but the number of streams that you can have open concurrently. How is that done? You have the initial unidirectional stream limit I talked about earlier. Those are the initial limits, but as soon as you've kind of blown those limits, you need to keep sending max stream frames to keep granting credit. So I think something we found in the early interop days is you could do some like quick tests like I just did, 1 or 2 requests and response interactions, all good. Then you run a server and you have a bug where you forget to grant new credits, and you eventually get to a point of kind of connection saturation and nothing can happen. Nobody can do anything and it idle timeouts, which is okay, but it's probably not what you want if you're running a service that's trying to run and run and run.
Yeah, so what's interesting, I think, about BGP to Lucas's point is that it tends to have extraordinarily long-lived sessions, and QUIC sessions will eventually run out. This is something that we did in HTTP 2 and also have done in QUIC. It's probably not likely in a protocol like BGP that you will run into these things, but who knows? Some of these boxes stay up for a long, long time. The thing that I think is probably more of a challenge in this context is managing keys and authentication, because I understand that BGP is often run essentially in the clear between different ASs, and that's going to be a shift in the attitudes in terms of how you configure the peering points that happen there, because you need encryption with QUIC. I don't know how many stacks currently use something like appreciate key mode. That is not something that is widely used on the web. So it may be that you end up in a situation where you want to use, for instance, self-signed certificates with maybe even no validation of them to ensure that it works as the existing system has done, with, of course, the option to upgrade to something that is fully authenticated.
Yeah, I was going to add that I'm happy to review a draft on BGP. I think it seems like an excellent use case. Key distribution seems like a problem, but yeah, there are a number of solutions. I think it's just a matter of looking through the options and getting a review from the QUIC folks and the transport bits, and then maybe getting a crypto review as well on whatever key distribution or lack thereof you choose to pursue. But it seems very doable.
Cool. Chris.
So when the example went up about how the handshake works, I saw that there was obviously some information in those initial packets. For example, I saw advertisements about what ALPNs we might be about to talk on. And obviously when I saw ALPNs in the clear, alarm bells went off. I was wondering what information all do we actually leak onto the wire in the clear, if that question makes sense.
Yeah, so as I talked about yesterday, we're not strictly leaking it in the clear. Anyone who is able to see the initial packets from the client and the connection ID that's in them, and they know the QUIC version that's in use, will be able to recover the keys and decrypt that information. So technically speaking, when we talk about what's in the clear in QUIC, that's often a shorthand that we'll use to sort of mean that, well, there's no genuine cryptographic protection for these things. We're just applying what is effectively AES as a checksumming mechanism and an obfuscation mechanism. So what's in the clear is everything that will be in the clear in TLS 1.3. And not a lot more, honestly. So if you look at TLS 1.3 and it's client hello and server hello, those are the things that will be in the clear. And so for the most part, that sort of falls into two categories. There's the things that you need in order to configure the key exchange in TLS. Those things will always be in the clear to some extent. But then there's also a bunch of configuration information from the client side, ALPN, some certificate related extensions, and also the SNI. Sorry? And yes, and at QUIC level, there's transport parameters, which is configuration information usually related to the operation of QUIC. And so the encrypted client hello spec will ultimately be able to take all of those things and provide some level of protection for them. There's all the debates about the availability of SNI. It's potentially the case that you could still put SNI in the clear and still protect all of those values at the same time. That's something that I think a lot of people sort of don't really understand about the value of ECH, is that it provides the ability to protect all of that sort of thing. That's coming, not yet.
Instead of extracting SNI from packets, if we can all move to Anycast, I know that's like asking for ponies, then you can just use the IP and like, please don't look in my packets.
Yeah.
But yeah, if I wanted you to look at the SNI, I would like staple it onto the front and like, so you could find it.
Yeah, I mean, just to follow up on opening the packets, I mean, we have RC 8999, which is the invariance draft, and that is sort of the working group's contract with the world on what will not change and what you should rely on. And to even say that like future versions of QUIC will use TLS 1.3 is not something I mean, I think, you know, someday there'll be TLS 1.4, I would think, and, you know, when that happens, we'll use it. So all this stuff is going to change as the protocol evolves. It's one of the key points of QUIC.
Thank you.
Anyone else in queue? Oh, I have one gotcha question that I had, you know, lined up in case nobody came up. So one of the things that I saw as a theme across all of the presentations was we tried this and then we realized we had to do this and then we realized we had to do this. Like the idea of building a transport protocol on top of a security layer on top of the transport protocol, that like this turned out to be super hard to do and was one of the reasons this was a really long effort. In what came out in QUIC version 1, in your opinion, whoever grabs the mic first, what is the sort of the hackiest part of the protocol and sort of like the undone work? Martin, take it. Unless Martin wants to take it. No?
The hackiest part?
Hackiest. I mean, if you misheard happiest, you can also do happiest, right? What's the happiest part of QUIC?
Well, for me, there's some pretty happy parts. We managed to get more of the protocol encrypted than I thought was possible at the outset. So that was a happy thing. Probably the hackiest and the part that I'm least confident in is connection migration. The security model for that is a little unclear, and the mechanisms that we have in place are not as thoroughly tested as I would have been confident with at the time. The way that we defend against various attacks is constrained to a very large degree by the nature of the network that we're dealing with, and so I'm not confident 100% that it will stand up to rigorous attempts to attack it.
I agree with Martin's sentiment. I can attest that connection migration works because we've default enabled it in quite a number of circumstances. And so like it does actually function as intended, but the attack surface seems very difficult to reason about. And I'm sure our implementation has something that you could do that would at least be annoying to a user, if not like problematic, but like at the very least, it's certainly not perfect. I can't think of anything else. I mean, there's a few decisions that got made that are annoying to me, but like I wouldn't call them hacky. They're just like implementation annoyances.
So I'd say that I thought you said the happiest part of the protocol.
You can answer that question too if you want to.
Right, that's what I thought you said. But the hackiest part of the protocol, I think that I don't know how to think about hacky, because the whole protocol is hacky in a certain way. If you, depending on how you look at it, I think of hacky as clever. So I think we did a lot of things that were clever in the protocol. But I'd say that the things that feel a bit fragile are both connection migration for sure, but also the handshake. It's robust. I think it's robust, but having, you know, the fact that I have to say I think is probably the argument there, right? So outside of that, I think the happiest part of the protocol is that we actually managed to encrypt fucking everything. It's like we got the packet numbers encrypted too, which was a joy.
Yeah, so I've been reiterating the thing on the handshake. I think we decided we were done with the handshake like 4 years ago, and then kept finding problems in corner cases and having to add a little more machinery. So like for me, the happiest thing about it is its extensibility. Like many of my colleagues here, spent a lot of time in TCP where it's like so hard to change anything for various reasons. And no, but it also leads to what I'm kind of most deeply concerned about, which is that, and they'll probably laugh because this is my hobby horse, but like version ossification, with the things that are, I mean, the question alluded to things we could read in the client hello. Between that and just this very readable version field, you know, people could just say, well, version 1 is fine and everything else, I don't know what that is, I'm going to drop it. And you know, that's something that we have to think a little harder on and come up with some solutions for to preserve that extensibility, because I think eventually you can get to a place where we get really big performance improvement. Well, we already have big performance improvements on TCP, but as the internet changes, QUIC can change in a way that the old tools can't.
And I think that's actually sort of like, I mean, we talk about this as it's a work, it's done, but it's a work in progress. And fortunately, we built a thing that can be a work in progress where we don't have to come back to it 30 years later. And I think that's the giant win. So on that, I've given myself the last word because we are at time. I would like to thank all of the presenters for their presentations and for the discussion. And all of our audience for joining us here at 7:30 in the morning. Your dedication to the internet is much appreciated. Please enjoy the rest of your week and see you around. Thanks a lot.
Thank you, sir.
Does that work for you, or is that a yourself? Can you do it on a phone, or do you need to? Oh, so it's an 18-minute walk. So you'd be leaving at like 11. You'd be leaving after an hour. It's up to you. Like, yeah.